So I'm part of the Joint Quantum Institute, which is a joint operation of both NIST and the University of Maryland. And within that, I'm part of the Laser Cooling and Trapping Group. And Gretchen Campbell is the leader of that group. Paulette, Trey Porto, Ian Spielman, Ida Tietzinger, and Charles Clark are all members of that group. And it's a pleasure for me to work with them. And we have support over the years from lots of organizations that you see here. Just to emphasize that the Joint Quantum Institute is supported by not just the University of Maryland and NIST, but also the Laboratory for Physical Sciences and the National Science Foundation through a Physics Frontier Center. Okay, why are we interested in using atomic gases to study condensed matter systems? Well, one of the reasons is that, that we can use these atoms to do quantum simulations of Hamiltonians that are important in condensed matter physics. And this is one of the ways in which one can address the complexity of a problem that is an important problem, but very difficult to solve numerically. You can have another quantum system emulate the behavior of the quantum system you're interested in, and that's one of the things that we do in quantum simulation. Atoms offer different opportunities for measurement and control than condensed matter systems do, and we'll see a little bit of that as we go along. Also, thinking about things from the perspective of atomic physics is different from thinking about things from the perspective of condensed matter physics, and we'll see some examples of that as we go along as well. And it's always interesting to study new systems, and sometimes nature doesn't give you some of the systems that we can make using atoms and lasers. So the basic tools of atomic physics, or atomic, molecular, and optical physics, as we often say of this field, are, on the one hand, quantum degenerate atomic gases like Bose-Einstein condensates and ultra-cold Fermi gases on the one hand, and optical lattices on the other. So what is a Bose-Einstein condensate? Well, I could give several hours of talks about Bose-Einstein condensates, but I'm not going to. I'm just going to give you some very elementary ideas about what a Bose condensate is. And if you want to ask questions about it, I'll be happy to answer them, but probably we'll save those questions for the end because they're extremely interesting, but probably not central to the things I want to talk about today. So we produce ultra-cold gases by laser cooling and by evaporative cooling. And we Bose condense using evaporative cooling as the last stage of cooling. We typically have many atoms, maybe as many as 1 million atoms. Some people have made condensates with 100 million atoms. Sometimes we make condensates that only have a few hundred atoms. But the point is that all of the atoms are in the same quantum state. They're in the same internal state, and they're in the same state of motion of their center of mass. The physical size of these objects is often macroscopic, on the order of 100 microns or even larger. This is macroscopic in the sense that the young people in this audience can see something that's 100 microns across. I cannot, but it's truly macroscopic in this way, many optical wavelengths in size. The interactions between the atoms can either be negligible or they can be significant depending upon what you choose to do and how long a timescale you work from. This allows you to change a problem from being simple, which is often the case when there are no interactions, to being complex, which is often the case when there are interactions. The key thing to remember is that in many respects, a Bose-Einstein condensate is like a gas at absolute zero. The other tool that we use for these studies is an optical lattice. An optical lattice can hold and manipulate atoms in a periodic array. So how does it work? Well, first, let's talk about the light shift. If I have a two-level atom, a ground state and an excited state, this is our favorite imaginary atom in atomic physics. And if you shine light onto this atom, and let's say for example, that the light is tuned to a frequency that is below the resonant frequency of the atoms, then the energy of the ground state is shifted down by an amount that is proportional to the intensity of the light and inversely proportional to the detuning from resonance that you see here. Now, imagine that I have two counterpropagating laser beams so that they interfere with each other to create a standing wave. Then that means that I have a periodic change in the intensity of the light. In places where the waves interfere constructively, I have a high intensity, and where they interfere destructively, I have a low intensity. And so I have this periodic arrangement of intensities with a period of half the wavelength of light. That means that I've got a shift in the energy of the atoms that is periodic in the same way, and the atoms can be trapped in this lattice, or they could move freely through the lattice depending upon the energy of the atoms and the depth of the lattice. And here's an important point. Because the depth of this lattice goes like the inverse of the detuning, and because photon scattering goes like the square of the inverse of the detuning, you can tune your laser very far from resonance, increase the intensity, and get a big light shift without having a lot of photon scattering. So we can make a periodic potential for the atoms that does not heat them, that does not scatter photons, which would heat the atoms, but that over the course of the experiment, which might be many seconds is a very long time for an atomic physics experiment, that over that course of many seconds, no photons are scattered, so that we can ignore the heating processes. We can just think of this as being a coherent periodic potential. Okay, so those are the key tools. Now, what are the wonderful features that make us want to do these kinds of studies? Well, one of the reasons is that this optical lattice, unlike the usual crystal lattice, is essentially free of dislocations and impurities. We might add defects, but they do not occur naturally. The lasers are so clean that you make a nearly perfect lattice. The atoms can be either bosons or fermions. If you're doing this with electrons and solids, you have no choice. They're fermions, and they're charged. We don't have to use that limitation for our atoms. They can be bosons, and for the things I'm going to tell you about today, they generally are. There are no, as I mentioned, Coulomb interactions, so no long-range interactions. We have contact interactions. We could arrange to have long-range 1/r³ interactions, but normally we don't. There are no phonons because our lattice isn't vibrating. It's made from near perfect laser beams. We might engineer phonons, but they do not occur naturally. We can vary the lattice constant. It can be as small as a few hundred nanometers, which of course is huge compared to the lattice constant in crystals, but we can make it larger than that at will if we want to, simply by changing the arrangement of the laser beams. We know what the potential is exactly, and we can control it. This is not usually the case for electrons in a solid crystal. You don't know what the potential is, and you can't change it because you have to accept what nature gives you. And we can change the dimensionality of the lattice. We can change the crystallography of the lattice. We can even make quasi-periodic lattices. It's easy to do that, where it's very hard to obtain these things in real crystals. So lots of things are interesting. Lots of things are not as good as they are with crystals, and we'll talk about that a little bit as well. Here's just an example of how I can change the dimensionality of a system. These three examples show how you could make a 1D lattice, which is a stack of pancakes, which are 2D systems. This is a two-dimensional lattice, which is an array of tubes, which are themselves 1D systems. And this is a three-dimensional lattice, which is the usual space lattice that we find in crystals. So it's a 3D array of zero-dimensional systems. So now let's talk about putting a Bose condensate, one of our tools, into an optical lattice, the other one of our tools. So we start with a condensate of atoms. I think that most of the things I'm going to show you today are sodium atoms. We Bose condense it using our usual tricks, which I mentioned before but didn't explain, in some sort of a harmonic trap, maybe a laser trap, maybe a magnetic trap. Then maybe we release it into free space, or maybe we keep it in the magnetic trap, and then we apply this periodic array of you might think of them as being miniature traps for the atom. So here is showing on the order of 10 such traps. There's probably more like 100 or 200 in our usual BECs, making an array of pancakes in a one-dimensional lattice. We just turn the lattice on, and now the Bose condensate is trapped in all of these different potential wells. Now, here is one of the key features of the way in which we extract information from this system. So pay attention to this slide. What we have done is taken a BEC, which is a completely coherent wave function, a single wave function for all these million atoms, a single wave function that extends over the entire 100 or 200 micrometer diameter of the Bose condensate. And we've divided it into a few hundred little slices, all of which are coherent, just like the original condensate. And then we turn the lattice off suddenly. So we have all of these different coherent condensates are now going to interfere with each other because everything is coherent. So they're going to interfere. And we get what is essentially a diffraction pattern. Here's the zero order diffraction. Here's the minus first order, the plus first order. These are obtained simply by taking a picture of where the atoms are after time of flight, because the nature of the diffraction is to add momentum to parts of the wave function. That momentum is sometimes called the crystal momentum or the reciprocal lattice momentum. In our case, it's exactly 2 times the photon momentum. The atoms absorb a photon from one laser beam, and they are stimulated to emit it into another, and that produces atoms given a certain extra momentum on one side or the other. Just to emphasize how deep the connection is to diffraction, I'm showing you a picture as a function of time for a Bose condensate that was exposed to a one-dimensional lattice, which is the equivalent of one-dimensional diffraction grating at time 0. And then we look at what it looks like at later times. And this is exactly what a laser beam would look like if I shined a laser beam into a diffraction grating and then looked at various distances along here. I would see exactly the same thing. Okay, now I think this might be a good time to stop for questions. So if any of you have any questions, I will be happy to answer them.
Very good. So colleagues, do you have any questions thus far? So just simply, if you want to unmute your microphones and ask directly to Bill, or simply raise your electronic hand via the part of the participants, I think, or via the part of the chat.
Yeah, or write something in the chat.
Or write something on the chat, and I'll read, of course.
Okay, so I just want to make sure everything's clear about how we start with a condensate, which is a coherent, very large macroscopic wave function. We apply light to it. That is a periodic potential, and we do diffraction. So, question.
We have one question.
Yes.
Miguel, please go ahead.
Hi, Bill. I have a question related to the detuning. So, something that has always eluded me is how large can you make the detuning before breaking down the 2-level approximation, for example?
Yeah. Well, okay. So the rotating wave that's what you asked about, the rotating wave approximation.
Not only in general, how large can you make it before breaking down, for example, the 2-level approximation or the rotating wave too?
Yeah, well, actually, since the atoms aren't two levels, the two-level approximation often gets better when you make the detuning larger. Let's imagine that I have an atom that has hyperfine structure and fine structure, which is what we have in sodium, for example. If my detuning is not large compared to either of those, then the fact that this is a multi-level atom will be very apparent. If I detune the laser by an amount that is large compared to both the fine structure and the hyperfine structure, then it will start to behave as if it were a two-level atom. If I keep detuning even more, then it will start to violate the rotating wave approximation, but I can still do it. People sometimes use CO2 lasers, which are off resonance by an amount that's almost equal to the resonant frequency itself, and it still works fine.
Okay.
So it's and it's a good thing, because if we could not detune a long way, then we would be bothered by a lot of photon scattering. So we're lucky that we can detune a long way. Thanks for that question. That was great.
Okay, thank you. Yeah.
There is a question actually, because I'm checking many things. So there is a question via Facebook. I think a student asked, can we manipulate diffraction patterns?
Okay, so I'm not sure exactly what that means, but we can create different kinds of diffraction patterns by using different arrangements of laser beams. So I showed you the most simple one. If I just use two laser beams to create a single standing wave, that produces this very simple diffraction pattern. Let's go back to here. If I were to use this array of laser beams, then I would create a diffraction pattern that would be parallel to the plane in which these laser beams are, that would be a two-dimensional array of diffraction spots, which is the same thing that would happen if you did diffraction of a laser from a two-dimensional diffraction grating, or if you did, say, diffraction of X-rays from a two-dimensional system like graphene. If I use a three-dimensional lattice, then I'll get a three-dimensional diffraction pattern in which momentum is transferred in all three coordinate directions, and I'll need to look along a direction that sees all of those different momentum components in order to really understand what's going on. And it could get as complicated as diffraction of X-rays from crystals. You know, if the crystals are complicated, the diffraction pattern is complicated too. So we can make more complicated patterns if we want to. For this talk, I'm going to be sticking to the simplest ones, but we often do things that are much more complex.
Excellent, thank you. I think we can continue.
Okay, let's go. So now, in order to understand the behavior of atoms in such a periodic potential, we're going to use the traditional tools that we already know about from solid state physics, namely Bloch states and band structure. Now, at the beginning of, or near the beginning of most solid state physics books, you'll see a description of the solution of Schrodinger's equation in a periodic potential. And you'll find that those solutions are called Bloch functions. And the Bloch functions have the feature that they're a function that is periodic in the period of the lattice, and then is multiplied by an exponential factor that looks very much like the wave function of a free particle with a momentum q in free space. And Q is therefore called the quasi-momentum, because it's sort of like momentum, but you've got this extra function that makes this thing not an eigenfunction of momentum. And if you ask what are the energy levels of of a particle that has this kind of a wave function, here's a picture of the energy levels. It shows that this is for a lattice that is not very deep, that doesn't perturb the motion of the electrons, or the atoms for that matter, very much, that it looks sort of like a parabola, but there are these famous band gaps near a momentum that corresponds to half of the reciprocal lattice vector, which is just the inverse the lattice spacing in momentum units, there's an energy gap where there are no atoms or no electrons that are allowed to have this energy. So that's, just in a few words, the kind of thing that you always read at the beginning of a book on condensed matter physics. And one of the important things to remember is this thing that we're calling the quasi-momentum can have added to it the reciprocal lattice momentum, which is h over the lattice spacing, and it doesn't change anything about the wave function, because if you add it to this term, it just changes it, changes the argument of the exponential by 2 pi, and of course that doesn't change anything, and it doesn't alter the nature of this function as well. So we can add and subtract reciprocal lattice vectors at will to this Bloch function, and it's still a Bloch function. Let's see. Now, I just wanted to emphasize that if we did not have the lattice, then this energy as a function of quasi-momentum would just be energy as a function of momentum. It would be a parabola that's the familiar kinetic energy of a particle in free space, namely p squared over 2m. Okay? Now, because we can add and subtract reciprocal lattice vectors, we can represent this energy level diagram in a different way. Instead of having a single parabola-like structure that has band gaps here at what we call the edges of the Brillouin zone, we can add similar parabolae that are displaced by a reciprocal lattice vector. So here's the principal one, the one that I was showing you before, and then here's another one, and then here's another one with having added a reciprocal lattice vector, 2 reciprocal lattice vectors on both sides. So here's one on this side, here's one on this side. Now, here's the thing that I want you to notice is the dashed lines are the original parabolae. The band gaps happen when those dashed lines cross. Now, we all know that in quantum mechanics, when you have 2 energy levels that cross, they don't cross, they in fact anti-cross if there's anything in the Hamiltonian that can couple the 2 energy levels. And that's exactly what's happening here. These 2 parabolae are anti-crossing here because they're a term in the Hamiltonian that couples them. And what is that term? It's what we call Bragg scattering. Here's an atom moving in the presence of 2 laser beams, one coming from the left and one coming from the right. One of the things that it can do is to absorb a photon from the laser beam coming from the left and be stimulated to emit a photon into the laser beam coming from the right. That will change the momentum of the atom by, I'm sorry about this, I don't know why when I operate my mouse, it also wants to advance the slides. It'll change the momentum of the atom by a reciprocal lattice vector, which is 2 times the photon momentum, by having absorbed and emitted a photon by stimulated emission. That reciprocal lattice vector, of course, puts the atom onto the other parabola, because the only difference between the one parabola and the other is 2 times the photon momentum, which is equal to a reciprocal lattice vector. So this is the physical mechanism that causes the coupling between the two states and causes these 2 curves to anti-cross instead of cross. Now, this was sort of a cartoon. Here is an actual calculation. You can see the remnants of parabola here. Okay, and here's another one here. It's kind of hard to see the central one, but we don't see the upper part here. That's at a very modest lattice depth, 5 times the recoil energy. The recoil energy is just the kinetic energy that you impart to an atom when it absorbs the momentum of a single photon. Here's a lattice that's 14 recoils deep. You'll notice that the ground band is almost flat. That is, on a scale where you can see the other bands, you cannot see the curvature of the ground band. It's completely flat. Now, the bandwidth is related to the tunneling. If the atoms don't tunnel at all, then the band is completely flat. And that's what these atoms are experiencing, that they don't tunnel or they hardly tunnel at all. That means they are firmly trapped in the standing wave. So I want you to imagine now a standing wave that I'm going to move. Now, how I do that, it turns out it's really simple. Instead of having two counterpropagating laser beams with the same frequency, I just shift the frequency of one of the laser beams a little bit. And now that produces what we call a moving standing wave. And if the atoms are trapped in that moving standing wave, then they will move along with it. So what we're going to do is we're going to turn on a standing wave that is moving. Now, if it's not moving, then it's just a Bose condensate, not moving with respect to the standing wave, and it has momentum 0 relative to the standing wave. But if the standing wave is moving, then it means that the atoms have a relative momentum relative to the standing wave. And in the rest frame of the standing wave, they have a quasi-momentum that's equal to minus m times the velocity of the lattice. So we're going to always think in the reference frame of the standing wave. So if it's moving, we're going to be working in a moving reference frame, and it means that it looks like the atoms have this value of a quasi-momentum, m times the velocity of the lattice minus the velocity of the lattice, because we're looking at it from the point of view of the standing wave. And this is just a little dissertation on the group velocity of the atoms. The group velocity is always the derivative of the energy with respect to the momentum. And if we use quasi-momentum instead of momentum, then we find that the group velocity is simply the curvature, that is the slope of the energy versus momentum curve. If the energy versus momentum curve is flat, then the group velocity is 0. If the energy versus momentum curve is just the free space one, p squared over 2m, then the velocity is just what you think it should be. It's the momentum divided by the mass, the ordinary velocity. So all of this is just what we would expect. Okay, now I want you to imagine the following situation. I turn on a lattice. It's very strong so that it holds the atoms at the bottom of each one of the potential wells. And now I start the lattice moving, and the atoms are dragged along. Okay. So I just want you to have that image in your mind, that if I start the lattice moving, then the atoms are going to be dragged along. On the other hand, if the lattice is very weak and I start the lattice moving, it won't do anything to the atoms. They won't be dragged along. Their group velocity relative to the lattice will be the velocity of the lattice, whereas here, the group velocity relative to the lattice will be 0, okay? Now, before we go on, I just want to see if you've got any questions about all of this Bloch state stuff and the idea of moving lattices and the way in which atoms will behave if the lattice is deep and if the lattice is weak, that is shallow. So, any questions?
Thank you, Bill. Any questions for this part? Colleagues, please raise your hand, or I'm controlling also the chat in Facebook and YouTube. If you have any questions, please go ahead. I think Salvador Cruz has raised his hand. Please, Salvador, go ahead. Thank you.
Yeah, thank you very much. Well, I'm just following very interesting analogy with what happens with the electrons and the lattice and the atoms in this effective lattice. One question is there an equivalent of an effective mass for the atom in this case?
Absolutely. Yes, yes. Okay, I'm glad you asked that question. So let's go to one of these pictures here. Now, if I have an atom here at 0 quasi-momentum, its effective mass is going to be much bigger than its free space mass, because the effective mass is essentially the second derivative of this curve, and it's going to be very small. If I go to an even deeper lattice, it's even bigger. Here, the effective mass is almost infinite. Now, let's go here. Here's the ground state. Okay, the effective mass is bigger than it is in the free space, but maybe not too much bigger, because it looks, it looks like it's pretty much the same as the curvature of the free space parabola. But here's the point that I want to make. If I now start the atom moving, we're going to talk about this a little bit later. In other words, I change its quasi-momentum, and I can do this just by accelerating the lattice. It'll come up here, and remember, it's the second derivative.
Yeah.
When it gets up here, then the mass of the atom is negative.
Yeah.
And the mass of the atom is going to be negative all the way down here until I get to the inflection point. Okay? Whereas with a parabola, you see, the mass is the same because the second derivative of the parabola is the same everywhere. So the mass is the same everywhere. But here, the mass changes from being positive and about the regular free mass to being negative and about the free mass, and then going back to being positive again. So the idea of effective mass is definitely important here. And it can do some really wonderful things.
Okay.
Oh, and another thing I should say is, I should have mentioned it. This idea that these band gaps are due to level crossings is not the usual way that condensed matter physicists talk about it. They usually talk about it, this is the solution of Schrodinger's equation in a periodic potential. But an atomic physicist sees this and say, oh, it's just level crossings. It's the same physics, of course, but it's just a different perspective.
Oh, okay. Thank you very much. Thank you.
Any other questions? Guys, I have some problems with Facebook and on YouTube because my laptop is going very, very slow, actually. So, this thing happens. So please, the other co-hosts, if you see questions in Facebook or in YouTube, just copy and paste in the chat so I can read them. Yeah. In the meantime, while I sort this thing out, so if there are there any other questions, colleagues? If not, let's continue. Thank you.
And of course we can always come back to any questions that we didn't get. Don't feel shy about posing a question, even though it's about something that happened a little earlier in the talk. Okay, so now I want you to imagine a kind of a story about atoms that are in an accelerated optical lattice. So let's imagine that the lattice is a kind of a conveyor belt, okay? So it's supposed to, here's the belt and here's some rollers, but at the moment they're not moving. The conveyor belt is flat, so that means there's no lattice. Or the laser beams that are making the lattice are vanishingly small in intensity. And I've got some atoms and they're sitting on the conveyor belt and they're not moving. So their velocity is zero. Now I'm going to turn on the lattice. So I imagine that there are some actuators in the conveyor belt that can make the conveyor belt into this periodic structure. And the atoms are going to settle into that periodic structure. And since the conveyor belt isn't moving, then the atoms aren't moving, okay? Now I'm going to turn on the rollers so that the conveyor belt starts moving. I'm going to turn it on very slowly and reach some final velocity, okay? And I'm going to call that VL for the velocity of the lattice. Obviously, the atoms are moving with the velocity of the lattice as long as the lattice is deep enough. So I'm asking you to imagine a deep lattice, something that would create a flat band so that the atoms are moving with the lattice. Now, I'm going to imagine that I suddenly turn the lattice off, okay? That's what happens when we do diffraction, right? Is we turn the lattice off suddenly. But this lattice is moving. So it's as if I've got a moving diffraction grating and I turn it off suddenly. Then what happens? Well, this is just to remind you of what's going on. I start with the lattice depth at 0, I turn it on slowly, and I keep it on at a constant value for a while. And during the time that I keep it at a constant value, I slowly increase the velocity, which is the equivalent of increasing the quasi-momentum of the atoms in the opposite direction. I slowly increase that velocity, and then I hold it at that constant velocity, and then suddenly turn off the lattice. Now, I think what I'm going to do, just so I'm sure that everybody understands what I'm doing, I'm stopping the sharing. So I want you to look at my image in the in whichever medium you're looking at. So imagine my fingers as being the optical lattice, and the atoms are trapped at the bottoms of the space between my fingers. Okay. Now I start moving my fingers along, and I reach some final velocity, and I'm having them move along at that final velocity. And then very suddenly, I turn the lattice off, and I wait for the enough time for the atoms to move someplace, and I look at where they are. That's what we call measuring a diffraction pattern. Okay, so now I'm going to go back to the sharing. I hope that I can do this without messing up. Okay, now let's see. Okay, so here's the diffraction pattern when the lattice isn't moving. We've seen this before. We have a central spot with zero momentum. We have some atoms that have -2 photons. We have atoms with +2 photons. This is the diffraction pattern. If the contrast were a little bit better, we would probably see a little bit of atoms here and here. You probably can't see it very well, but that's just because not many atoms are diffracted into the higher momentum state. Now what happens as we make the final velocity of the atoms non-zero? And the answer is it's still a diffraction pattern. The atoms' velocities are still multiples of the reciprocal lattice vector, but the weight of how much is diffracted into each momentum changes with the lattice velocity. So when the lattice velocity is 2 photon recoils of velocity, that's 6 centimeters per second for sodium, then it turns out that the average momentum of the sodium atoms is the same. That is, it's 2 photon recoils. You see, here's most of the atoms are at 2 photon recoils. We got some that are 2 photon recoils higher and some that are 2 photon recoils lower. Remember, the only momentum the atoms can have is some multiple of 2 photon recoils, because the only thing that can happen to the atoms is they can absorb and emit photons. And they always have to both absorb and emit. And so, because that's what leaves them in the ground state. And so the momentum of the atom always has to be multiples of a reciprocal lattice vector, which is 2 photon recoils. And when the lattice is moving with 2 photon recoils, the average velocity of the atoms is 2 photon recoils. That's perfectly reasonable. The atoms are moving at 2 photon recoils. You turn off the lattice, they're still moving with 2 photon recoils. It's just that the distribution isn't all in a single momentum, because we've done this diffraction process. Okay, and here's just the experimental realization of that. It's not exactly a straight line because the atoms are not in a perfectly infinitely deep lattice, but you can see that it's essentially linear in the lattice velocity, just as you'd expect. Okay, now that made perfect sense. Now I want you to imagine almost the same experiment, but just a little bit different. So again, we start with a flat conveyor belt, no lattice. The atoms are at 0. We turn on the lattice at 0 velocity, so the atoms are trapped. We start the conveyor belt moving. We come up to some final velocity. The atoms are dragged along at that final velocity. But now we're going to turn the lattice off, but we're going to turn it off slowly. And just to make sure that everybody's got the thing, again, this picture of me with my hands. Okay, my hands are the optical lattice. This is the bottom of the lattice where the atoms are trapped. Now I'm imagining that I've loaded the atoms up and I'm slowly accelerating the lattice until I reach some final velocity, and then I stop at that velocity. That is, I'm now going at a constant velocity, not accelerating anymore. And while I stay at that constant velocity, I very, very slowly turn the lattice off while it's moving at that final velocity. That's the new experiment. Okay, now let's go back to the sharing the screen. Okay, now, Now, what I want you to do is to predict what the answer is going to be. Now, if we were doing this live, I would have you raise your hands. So maybe you can raise your hands and somebody else can look and see whether you're raising your hands. I can't because I'm looking at my slides. How many of you think that the velocity of the atoms, let's say the average velocity of the atoms, is going to be the velocity of the lattice, like it was in the previous case where I turned the lattice off suddenly? Now I'm going to turn the lattice off slowly, and the first choice for an answer is that the velocity is going to be the same as before, the velocity of the lattice. So how many people think that? Okay, second choice, 0, just because it's a nice round number. Okay, how many people think that the velocity will be 0? Okay, how many people think that it will be something in between the velocity of the lattice and 0? Because after all, you might think that if it's not one or not the other, it might be somewhere in between. So the fourth choice is don't know. And the last choice is none of the above. Okay, so I hope everybody has made a choice. Now, if we were in person, let me tell you that except for the people who have already heard a talk like this before, most people will say that they don't know. A reasonable number of people will say it's going to be the velocity of the lattice. And a reasonable number of people, just a few people, will say some of the other ones. Okay, the correct answer is none of the above. And now I'm going to show you why. First, I'm going to show you the data. So before showing you the data, let me show you again the sequence of events. So here's the depth of the lattice. We turn the lattice on slowly. We keep the lattice on a constant depth. While it's at a constant depth, we ramp the velocity up, okay? And we keep the velocity constant while we ramp the lattice back down. And then we wait and we see what the diffraction pattern looks like. And this is what the diffraction pattern looks like. If the lattice velocity is less than 1 recoil, that's 3 centimeters per second for sodium. If the lattice velocity is less than 3 centimeters per second, the velocity of the atoms is 0. All the atoms have 0 velocity. As soon as the velocity of the lattice becomes bigger than 3 centimeters per second, which is 1 recoil velocity, all the atoms have 2 recoil velocities until the velocity of the lattice gets to be 3 recoil velocities. And then as soon as it's just a little bit more than 3 recoil velocities, then the velocity of all the atoms is 4. And it just keeps going up in a staircase like that. Now, what is going on? Well, what's going on turns out to be pretty simple, even though it seems pretty complex. It's called Bloch oscillations, or at first we thought of it as being Bloch acceleration. If I'm in the lattice frame, and remember, we always want to think in the lattice frame because that's where it makes sense to think about quasi-momentum. In the lattice frame, as we accelerate the lattice, the atoms start from a quasi-momentum of 0, and they increase their quasi-momentum as we accelerate the lattice, okay? Now, let's say that we go up here to some place that is at a lower velocity than 1 photon recoil. That's here where the crossing happens, okay? We go up and we're here and we stop accelerating so that we're sitting somewhere here on the curve. And now we adiabatically turn the lattice off. That means we're going to go from this energy curve to this one because that's the one that is the right curve for this quasi-momentum. And remember, we're in the lattice frame. So the quasi-momentum of the atoms in the frame of the lattice is just minus the velocity of the lattice. And when we transform back into the lab frame, we see that it's 0. That's why all those atoms had 0 velocity. But look what happens if we just cross over to just the other side. Then when we turn it off, the curve that we adiabatically connect to is not this one, but this one. And that one has 2 units of photon momentum because it's just this curve that we constructed from this curve by adding a reciprocal lattice vector, which is 2 photon recoils. Another way of thinking about it is that the atom moves along here, gets to the edge of the Brillouin zone where it satisfies the condition for Bragg scattering. It Bragg scatters, that changes its velocity by 2 photon recoils or 1 reciprocal lattice vector, changes its velocity from here to here, and then it continues along. But this point is absolutely identical to this point, and going down here is absolutely identical to going along here, because this whole picture is absolutely periodic in a reciprocal lattice vector, because nothing changes when you change 1 reciprocal lattice vector. That's what we learn from the Bloch functions. Okay, so those steps, that staircase that we saw in momentum, is in one picture at least due to Bragg scattering at the Brillouin zone boundary. And if we view it in the lattice frame, these are what people call Bloch oscillations. Bloch oscillations are what happens to particles moving in a periodic potential when you accelerate them. So if these were electrons, you would just apply an electric field that would accelerate the electrons. When they accelerate to get to a velocity that puts them at the edge of the Brillouin zone, they Bragg scatter, they reverse their velocity, and then they start accelerating again. And that process of increasing the velocity due to the electric field, then reversing the velocity due to the Bragg scattering, then increasing it again, that's called Bloch oscillations. It's very, very hard to see Bloch oscillations in electrons and crystals because there's just too many things going on, phonons and scattering of electrons from other electrons and impurities. Very, very difficult to see it. In optical lattices, it's the easiest thing in the world to see. So here's an example of something that's really hard to do in solid state and really easy to do with atomic physics. So, well, here, this is just another depiction of how Bloch oscillations work, but let's not worry about it. The steps that we observed in the lab frame are oscillations when we observe them in the lattice frame. And that's all I want to say about Bloch oscillations. Now, here's the thing that I think is the really important message of this talk that I'm giving you. So far, I've been telling you about atoms and ignoring the interaction between the atoms. That means it's a single particle problem. And even though some of these things might not have looked as if they were very easy to figure out, normally single particle physics is simple. And in fact, once you know what the tricks are, it's easy enough to figure out the results of single particle physics. It's not so easy to find the results of many particle physics. Sometimes there are tricks like mean field theory that you can use to solve many body problems, but a lot of times there isn't. So here's the real interest, is when we have multiple particles, many bodies, and that we can't use tricks that simplify the problem into single particle physics. So if there are any questions about what we've gone to so far, I'd be happy to answer them. And if not, we'll go on and we'll talk about many body physics for just a few more minutes. So questions?
Very good. Any questions, colleagues? There were some questions that the co-host put on the chat. Well, I'll read them. So I think Adrian Escobar, you have a question? Please, Adrian, unmute your microphone and go ahead.
Oh, yes, thank you, Isaac. So just a small question. Can we mimic using these devices, the so-called time crystals, or only the normal crystals?
Yeah, that's a really good question. So as you probably know, time crystals are, the idea behind a time crystal is that you want to have some kind of spontaneous symmetry breaking that will produce a behavior that is periodic in time, in the same way that these crystals, I don't mean these crystals, but solid state crystals have a spontaneous symmetry breaking that produces something that's periodic in space. That's what a time crystal is supposed to be. It turns out that you can't actually do it. After the original proposal, it was then proved that it's impossible. So what people now call time crystals are ones where they've already imposed a something that breaks time symmetry. And then there's an additional breaking of the symmetry that produces a superlattice in time. So for example, if you have something that occurs at a certain frequency, then there's something spontaneously happens that causes something to happen at half that frequency. That's what time crystals mean today, at least as far as I understand it. Now, let's talk about what happens here. So one of the key things to remember, and I'm so glad that you asked this question, is that these atoms do not order themselves. These atoms are ordered externally. That is, we impose the order externally. There is no spontaneous symmetry breaking here, at least not so far. So what we have done here is to impose a spatial order, and the atoms simply fall into it. That's why we call it a lattice and not a crystal. So these atoms are not forming a crystal. We are creating a lattice into which the atoms fall. Now, to answer your real question, which is, can we do something that is the analog of what goes by the name of time crystals today? And the answer is yes, under certain circumstances. For example, I could make a lattice, impose the spatial structure, and then allow the interactions between the atoms to create an additional structure. For example, let's say that the atoms had spin, and sometimes we do experiments with atoms that have spin. And let's say that the spin-spin interactions, usually caused by some kind of exchange force, is antiferromagnetic. We could have a situation where the atoms arrange themselves into an antiferromagnetic order. And in my opinion, that Néel ordering that's an antiferromagnet would be the space equivalent of what today is called a time crystal. Now, whether anybody else would agree with me that this is the space equivalent of today's time crystals, I don't know, but that's my opinion.
No, impressive. Thank you very much, Phil.
Thank you, Adrian. There is another colleague, sorry, I don't recognize. It's Aula CBI 146. Please go ahead.
Hi, my name is Luis Hernandez. I just want to ask a couple of questions, just more in the experimental side of your extraordinary talk. Thank you very much for it. But two things: when you are creating the lattice, you have problems with filling factors in your experiments.
Yeah.
That's one thing. The other one is when you create your conveyor, when you move the lattice, what do you use to do it? And especially like modulator, you change the frequency of one of the beams. I don't know what to do. And just final question, just your opinion on this matter, because it's not the goal of your talk, but some years ago, in your colleagues in Colorado, the ion trap group there have created what they call ion crystals in penetrants.
Yeah.
Do you think that kind of, I know that you can go to very low temperatures in ion traps. Of course, you cannot create Bose-Einstein condensate with these traps, but can you mimic some of the physics you are doing with these kind of ion crystals?
Okay, thanks. Those are great questions. So please stay on, because since you asked 3 questions, I want to make sure that I do indeed answer each one of them. Okay, so the first question about filling factor. Because I've been so far talking about things where I ignore the interactions, then filling factor has nothing to do with any of the experiments that I've shown so far. Now, in fact, you've anticipated what I'm going to show next, where filling factor will be very important. And we will rely on many body effects to produce a perfect filling factor. But so far, this was two-dimensional pancakes in a one-dimensional lattice, and it just didn't make any difference how many atoms were in each one of those pancakes. So the filling factor is irrelevant because the whole physics is just n times what the single particle physics is. But in what comes next, filling factor is very important. Okay, so the next question was, how do we make the lattice move? You anticipated exactly correctly the right answer. We shift the frequency of one of the beams. Now, from a practical standpoint, we're very often using acousto-optic modulators to manipulate our laser beams. We use the acousto-optic modulators to turn the laser beams on and off and to modulate their amplitude. We can feed the acousto-optic modulators with different radio frequencies. And then, so for example, it's pretty common for us to use modulators that have a carrier frequency of a few tens of megahertz. It's a pretty common and cheap modulator. So on one of them, we might have 10 megahertz. And on the other hand, we might have 10 megahertz plus 25 kilohertz. And that plus 25 kilohertz can be come from a synthesizer, and that synthesizer can be made to sweep the frequency. And so that's how it's done. It's all done at the radio frequency level rather than at the optical frequency level. So it's really easy to do these manipulations. And the final question was about ions. Yes, so those ion crystals are very different from the kinds of arrays that we make. For one thing, they are self-organized because it's it's a kind of I'm trying to remember what the name of when charges self-organize themselves. There's a certain kind of lattice that's called, and they have found, I think before they actually did the numerical calculations, they have found that the structure of the crystal structure of these things is not at all simple. It's not what you would have guessed, but depends upon the nature of the trap. These traps are often quadrupole traps, and they have seen that the basic structure depends upon the boundary conditions for these clouds. So they've learned things that I don't think they anticipated learning at all. So really interesting new physics has come out of those things, but it's a very different kind of physics from the physics that we're doing. In general, as you pointed out, you can't make Bose condensates because the ions are so firmly positioned by the Coulomb repulsion of the other ions that there's very little quantum tunneling from one site to another, and so you don't get the kind of quantum effects that are routine in the experiments that we do, or in experiments in condensed matter physics where electrons tunnel from one lattice site to another. So those are really wonderful experiments, but they explore a different kind of physics typically than the ones that we explore.
Thank you.
Thank you. Miguel has one question. Go ahead, Miguel.
Yes, so I have a question related to the Bloch oscillations. So instead of using a space modulator, could it be possible to tilt, for example, the lattice and use the gravity?
Yeah.
And what would be the difference?
Absolutely. And in fact, people do this. So, yeah, well, I guess Einstein told us that an accelerated frame is exactly equivalent to gravity. So I'm going to have to agree with Einstein and say that there's no difference in principle from putting an optical lattice into a gravitational field. In other words, arranging it so that it's ranged vertically. There's no difference in that than there is in having the whole thing arranged horizontally and accelerating the lattice in the horizontal direction. I think that the principle of general relativity is that gravitational fields and uniform acceleration are equivalent, so it has to be the same thing. And people are, in fact, using these Bloch oscillations to do things like measure the acceleration of gravity, because the rate at which the Bloch oscillations happen is related to the acceleration. At this point, I don't believe that these measurements are yet competitive with are something that's going to be of increasing interest as time goes on.
But is there any practical advantage of using the space modulator instead of tilting the lattice, or I mean, from the experimental point of view?
Yeah, it's easy for us to make the acceleration as big as we want. So the acceleration of gravity is not very big.
Okay, I see.
So if we want to, for example, other people have used this technique of Bloch oscillations or Bloch acceleration to give atoms a huge amount of momentum in order to do interferometry with widely separated momentum states. This can be really good for making an instrument that measures inertial forces like rotation using the Sagnac effect. And in order to make this work efficiently, you want to give the atoms a lot of velocity quickly. So we want a big acceleration, and we can get bigger accelerations this way than with gravity.
Okay, thanks.
Yeah.
Thank you. Shall we continue?
Sure. Okay. So right. So now I want to talk about many body effects. There is a phase transition called the Mott insulator transition. The quantum phase transition, let me not go into what that means, but it's driven by interactions between the atoms. And it is one of the things that determines, for example, whether their systems are insulators or conductors is determined by what side of the Mott insulator transitions they're on, but it's very difficult in a condensed matter system to actually see them. And it turns out it's pretty easy to see it in atoms. The thing that governs this Mott insulator transition is something called the Bose-Hubbard model. Normally, you would have learned this as just the Hubbard model because in condensed matter physics, it's always fermions, it's never bosons, but we can have exactly the same model with bosons. And here's the model. It's an extremely simple model. We've got a periodic potential. There it is, okay? We have particles in the periodic potential. We only have two parameters. One parameter is what is the tunneling rate to go from one site to the next? And the other one is what is the energy cost to have two particles on the same site? So if we imagine that when there's two particles on the same site, that they repel each other, then there's going to be an energy cost for putting two things on the same site. And these things compete with each other. The tunneling makes the atoms want to go from one place to another, and the repulsive on-site interaction makes them want to stay where they are. If the tunneling is big, which would be the case if the lattice is weak, and the interaction energy is small, which would be the case if, well, just if the atoms don't interact very strongly, then the tunneling wins, and the atoms are going to behave as if the lattice wasn't there. They're just going to freely tunnel, and it's going to look like a Bose-Einstein condensate. But if the tunneling is small and the interaction strength is strong, then what that's going to mean is that atoms are going to want to stay where they are and not tunnel over to the next site. And the lowest energy configuration is going to be one atom per lattice site, assuming that there are enough atoms around to fill up the lattice. Now we get to this issue about filling factor. So if we can arrange things so that there are enough atoms to have one atom per lattice site, then if the on-site energy is big and the tunneling is small, then you're going to have one atom per lattice site. And if you make the tunneling large and make the on-site interaction small, then you're going to have an ordinary Bose-Einstein condensate. And the great thing is with the atoms, we can go from the one to the other easily because it's easy for us to change the depth of the lattice. We can also change the interaction strength, but that's not as easy to do. So usually these experiments are done by changing the depth of the lattice. The Hamiltonian is extremely simple. Here's the tunneling term. Here's the interaction term. If you want, you can add an overall potential, which we often do because the atoms are held in some sort of a trap. This is one of the simplest models you could imagine. And it turns out that it's extremely difficult to solve this problem numerically. You cannot solve it by brute force for more than a few tens of lattice sites. And only recently have people been able to use quantum Monte Carlo methods to solve this for bosons, and no one knows how to solve it for fermions. This is just some early work about what the phases would be, but this didn't figure out what the transitions were. Numerical simulations, as I said, with quantum Monte Carlo have done that recently. Here's the general idea. When the tunneling is big, as I mentioned before, compared to the on-site interaction, it looks like a Bose condensate. The atoms are everywhere. Every atom is on every site. But when the tunneling is small compared to the on-site interaction, then we have one atom per lattice site if we supply the right number of atoms. And here's the experimental proof. When the lattice is weak, so that we have the superfluid phase, then when we turn the lattice off, we get a diffraction pattern because this superfluid phase or this Bose condensate phase has the same quantum phase. So I'm using the word phase in two different ways. It has the same quantum phase across the entire lattice, and that produces this diffraction pattern. But when I make the lattice deeper, then I have one atom per site, and you might think of this as being the number phase uncertainty principle. If I know exactly how many atoms there are, one, then I have no information about its quantum mechanical phase. So that means that I essentially have a random phase, and so the diffraction pattern disappears. And if we look very carefully at where the diffraction pattern disappears, boom, we can see exactly where the phase transition is, and it turns out it agrees essentially perfectly with the quantum Monte Carlo calculations. And the beauty of this, to continue to address the question about filling factor, if you do this in a harmonic trap, the atoms adjust themselves automatically to have the right density to produce a filling factor of one atom per lattice site at the center of the trap. And then outside of that, you have essentially no atoms. And it's wonderful. It's just like magic. So we've come to the end of the talk. I don't want that we only do these kinds of experiments in my group at NIST. These kinds of experiments are being done in laboratories all over the world, and all sorts of wonderful things that are different from the kinds of things that I've been telling you about are going on both experimentally and theoretically in places all over the world. People are using atoms to do condensed matter problems that aren't lattices, for example. So, for example, the late great Debbie Jin examined the BC-SBEC crossover in a Fermi gas without an optical lattice, but studying a really important problem in condensed matter physics. And one of the things that I find so satisfying about this work is that we have condensed matter physicists and condensed matter experimentalists collaborating with AMO experimentalists and AMO theorists to learn new kinds of things. And so just to give you a little bit about other kinds of things that are going on in my own group, the group led by Gretchen Campbell, making synthetic fields, synthetic magnetic and electric fields for atoms, spin orbit coupling, that is coupling the momentum to the spin of the atoms, making superfluid circuits analogous to squids and Josephson junctions, making spinor quantum phase transitions, that is ferromagnetic and antiferromagnetic transitions, making superlattices. These now are superlattices where you impose the superlattice as opposed to superlattices where they're self-organized. And these people, Gretchen Campbell and Ian Spielman, Trey Porto and Paulette, are doing some of these amazing experiments here. And as I said, all over the world. And so we dream about using these kinds of things to do new kinds of quantum simulations, to study topology, to study things like Majorana fermions. And so I leave you with the conclusions that cold atoms and optical lattices are a new way of studying the motion of things in a periodic potential, and that even at the single particle level, the kinds of things that we do can lead to some rather non-intuitive behavior. Some phenomena like Bloch oscillations and the Mott transition that are difficult or impossible to observe in solids can sometimes be seen easily in lattices, that quantum simulation is really becoming a reality, and that we can have some unique properties. We can't do everything that condensed matter can do. We can't measure things like conductivity very easily, for example, but other things that condensed matter systems have a hard time doing, we can sometimes do easily. And so we're coming to the end of the talk, but it's not really the end because there are so many new things left to do. And I thank you so much for the questions that you've raised so far, and happy to answer some more.
Thank you very much, Bill. Colleagues, any other questions you may have for Bill? I have some questions myself, but first I would like to give the opportunity to the students and other colleagues. I don't see hands being raised. Okay, so let me ask you one question, Bill. It's more like a just, well, you have done already this type of some experiments. So sometimes in certain systems you have localization, delocalization transitions, which you might think is something similar to you have in the Bose-Howard model. But in some cases, in some models, in particular, for instance, in random matrix theory, you have an intermediate phase, which is normally called a phase which is delocalized and yet non-ergodic. That means that the localization is in a finite fraction of the lattices to a given exponent. Would it be possible in your experiments to accommodate for that, perhaps introducing some disorder?
Yeah. Well, I haven't done these experiments, but there are people who have done experiments where they add disorder to the lattice. Remember at the beginning, I said that our lattices are perfect. Well, it's not quite true. There is a little bit of variation of the depth of the potential from one lattice site to another. But usually that's not enough to induce something like an Anderson localization, which I think that's what you're talking about, is Anderson or Anderson-like localization, maybe Andre Arbre or something like that. So people have done that deliberately. So there's two classes of experiments that I'm thinking of in which people have deliberately added disorder. One is you take laser speckle and you just shine the laser speckle onto your lattice. So laser speckle is a good random feature, and so it really seems like the right kind of thing to do when you want to put something that's truly random. The other one, of course, is the quasi-random thing that you get by imposing on the lattice another incommensurate lattice, so that it looks sort of quasi-random how the depth of the lattice changes from one lattice site to another. So those two ways of doing things have both produced results that show a kind of Anderson or quasi-Anderson localization. And yeah, so this is being done. And as far as the details, I'm not sure I can tell you more than what I've already said, but as far as being able to see what fraction is localized and what fraction is not, yes, that is a routine thing. You look at the distribution of atoms after some time of evolution, and you can see that a certain fraction follow an exponentially localized functional form, but that doesn't necessarily apply to everything, depending on what the conditions are. Just as you described, you could have a partial localization, that some fraction of the atoms are fully localized, but you see, there might be a threshold. If the momentum of the atoms is above that threshold, then they won't be subject to the localization. And depending on what kind of localization you have, it may or may not have a threshold. So yes, you're absolutely right. These kinds of things are being studied. It's just that I don't know that much about them.
Thank you, Bill. Any other questions, colleagues?
Hi.
Salvador, please go ahead. Do you have any questions?
Well, thank you very much for this splendid lecture, Professor Phillips. I have one question. How would you imagine to introduce lattice vibrations in this model that you, this presentation that you have given us, in order to introduce phonon scattering effects on the different collective states of the system?
Yes, so it is something that we have imagined, and but we haven't really done it yet. So there's two reasons why we haven't done it. So far, we've just been so thankful that we don't have phonons, that we're happy to continue on in that sort of delightful paradise where we don't have real phonons. The other reason is it's not that easy to create something that looks like a phonon. So we already have some vibration of the lattice, but it's not phonon-like at all. In other words, what we have is vibrations of the lattice where the entire lattice moves together.
Yes.
And that's not what happens in phonons. And it happens for us because we're in a laboratory. There are mirrors. The mirrors vibrate. And so that means that the phase of our laser beams is going to move around, but typically it doesn't matter, because typically our lattice is deep enough that the characteristic frequencies in the lattice are high enough compared to the characteristic frequency of the vibration of the lattice that they just follow along adiabatically and we don't have to worry. And if that's not the case, then we just take a little bit more time, we spend a little bit more money, we demand more of the graduate students, and they get rid of the vibrations.
Okay.
But we've certainly been thinking, so how could we make real phonons? So we're thinking about a kind of thing where we might impose onto the lattice an additional modulated intensity at a different wavelength, and then move that modulated intensity in such a way as to mimic the behavior of a phonon with a particular phonon momentum. But we haven't, at least in our group, we haven't gone any further than just sort of imagining what might be required to do it, as opposed to really sitting down and thinking about it carefully. But it's something for the future.
Thank you very much.
Thank you. Very good. Miguel, please go ahead.
Yes, so I have another question, and this is related to the light-matter interaction. So, I mean, at this point, light-matter interaction is, sorry, the role of the light is just to create the potential for the atoms, right?
Yeah.
But I guess it's possible to put the lattice in a cavity in order to reach a strong coupling and then get polaritons. No?
Yeah, yeah.
And yeah, then I was wondering, because I found very interesting the fact that you can change the effective mass of the atoms to make it a negative, and also it will you could make a polariton with a negative mass, right?
Yeah.
So has this been done before?
So again, you know, I'm not as familiar as I wish I were about all of these things, but people are doing wonderful experiments with polaritons in a way that I would say is fitting somewhere at the intersection of condensed matter physics and optical physics, because the polaritons, as you know, are half atom and half light.
Yeah.
And as a result, you can manipulate their masses by making them more like other people who are doing things. So yes, these kinds of things are going on, and we're now starting to look at polaritons in a Rydberg gas. So now this has become more atomic physics, where we're borrowing the idea of polaritons from condensed matter physics and putting it into a gas phase experiment. The idea here is very similar to the kind of polaritons you're probably thinking about with excitons and photons, where we couple a cold gas of atoms into a Rydberg state, which would be sort of the equivalent of making an exciton or an excited state of an exciton, depending on what you're doing. And then, because of the fact that the Rydberg atoms have extremely strong interactions between themselves, because of the very high polarizability of the Rydberg atoms, they have much bigger van der Waals interactions, as well as sometimes resonant dipole-dipole interactions.